So hello, everyone. Thank you for joining this webinar entitled MDPI International Mother Earth Day Webinar 2025. And I am Dragana Panic, and I will be your host on behalf of MDPI. I will share my screen with you just to help me out with this presentation. Okay, before we start with the webinar, I would like to say a few things about the MDPI and about the Geosciences Journal. So as you can see here, MDPI is a pioneer in scholarly open access publishing, and it has supported academic communities since 1996. MDPI is based in Basel, in Switzerland, and MDPI has the mission to foster open scientific exchange in all forms and across all disciplines. We have more than 469 diverse and open access journals, including 460 peer-reviewed journals and 9 conference journals. And all of those journals are supported by more than 295,000 academic experts who share our mission, values, and commitment to provide high-quality services for our authors. When it comes to the Geosciences, Geosciences International peer-reviewed open access journal on geosciences, future Earth, and planetary sciences that is published monthly online by MDPI. It covers a wide range of topics related to Earth sciences that includes geology, geophysics, atmospheric sciences, hydrology, and environmental sciences as well. The journal aims to promote the interdisciplinary research and to provide a platform for innovative studies on Earth's process and resources. Geosciences index in major databases such as Scopus, Web of Science, and GRF to ensure high visibility for published articles. The journal maintains a rigorous peer review process and offers fast publication timelines. With its commitment to open access, Geosciences supports the free and global exchange of scientific knowledge. This will be the program of today's webinar. After I introduce our speakers, I will hand the floor to Professor Caroline Nemeth, and then after that presentation, you can ask questions if you have anything to ask for Professor Caroline Nemeth. Afterwards, I will give the floor to Professor Brandon McKay, and of course, after his presentation, we will have a small Q&A session. Then we will close the webinar around 10 a.m. At Central European Summer Time. If you want to submit your research to a special issue that is related to this topic, you can see here 4 proposed special issues. And the first one is led by our speaker, Professor Caroline Nemeth. And if you have any questions for our speakers, you can post them in Q&A box at the bottom of your screen and anytime during the webinar, and I will suggest you to address the name of the person to whom you're addressing your question. Also, as the participants of this webinar, you will be able to download an electronic certificate of attendance by accessing your dashboard on sciforum.net after the webinar ends. The certificate can be found under My Certificates at the Sciforum. Now, I would like to introduce our first speaker, Professor Caroline Nemeth. Professor Caroline Nemeth is a geologist that is specializing in sedimentology, volcanology, and geoheritage. He was a professor at Massey University, New Zealand until 2022, and now holds an adjunct professor position there. Since 2024, he has been a doctor of Hungarian Academy of Sciences and is a senior researcher at the Institute of Earth Physics and Space Sciences in Hungary. He also serves as a research affiliate in the Istituto Nazionale di Geofisica e Vulcanologia in Bologna, Italy. Professor Nemeth earned 2 PhD degrees, one in geology from the University of Otago and another in environmental sciences from the University of Sopron. His global fieldwork has focused on monogenic volcanism and the relationship between volcanism and sedimentary processes. Currently, he chairs the IUGS subcommission on geological heritage sites, and he has played a significant role in geoheritage research and UNESCO Global Geopark evaluations worldwide. And now it is my pleasure to invite Professor Nemeth to deliver his presentation.
Thank you, Dragana. This is really a very nice introduction, so save lots of time for me. And now I try to share my screen, and I hope that everything will be. Yes, looks all right. Everybody can see everything. Is it okay?
Yes, everything is okay, Professor Nemeth.
Yes, thank you, Dragana. So welcome everyone for this webinar. I just realized when I was preparing this presentation that the slide number is definitely more than the 30 minutes would allow, so probably I will skip few of the slides, but I try my best to keep everything intact and meaningful. When I've been asked by MDPI and Geosciences, which is a premier journal of the MDPI clan, I was actually really excited because of how they call this MDPI International Mother Earth Day. And I think the 22nd of April is essentially the Earth Day, if you put in that way. It's a very significant event, but actually endorsed by UNESCO and many other international geoscience societies. And I think it's very appropriate to talk about geoheritage. So I decided to actually present something about geoheritage as the building block of geodiversity of Earth heritage. And you can see in this title that I use this word geoheritage versus Earth heritage. And this is reflecting my background, like what Dragana really explained very well, that I'm a geologist. I'm basically trained as sedimentologist, wandered to the petrology, petrography, geochemistry, volcanology, magmatology, and so on, and spend lots of time on understanding of the Earth systems from the magmatic perspective. And then, after more than 15 years, I actually discovered that by myself that basically doing something for the common and for the community, it's really actually very, very good to do some kind of research on geoheritage. I don't really want to talk about, all those things, my affiliations. And you see here one sign in my slide, the second 100 IUGS geological heritage sites, which is an ongoing project, an ongoing process, what I'm actually looking after at the moment, which is an IUGS, the International Union of Geological Science projects, which is a very successful project. The first 100 really selected amazing geological heritage sites. And now we are going to the third one after the second, which was actually announced in August in the last year. I will talk about all those processes later on, and you will see how the geoheritage, geodiversity, and Earth heritage connecting into this big global phenomena with the IUGS, one of the most successful Earth science or kind of a learned society on Earth, actually promoting in these days. I hope that I can find the next slides. Yeah. So before we are going into the understanding all these processes, it's very good actually if we actually looking through the geodiversity as well versus geoheritage. What's their meaning of them? Geodiversity in general is defined as a natural range or diversity of geological, which means rocks, minerals, and fossils as the most important was, geomorphological and landforms, topography, physical processes, soil and hydrological features on Earth. It includes their assemblages, structures, systems, and contributions to the landscape. From this slide, you can see two or actually three diagrams from the Scopus, how actual geodiversity research look like in these days, looking at, what are the main countries where geodiversity research actually really very highly promoted, what are the authors, what you can see in general in the global literatures, and what number of documents we actually see per year. Actually, the number of documents per year or per source is obviously need to be taken care, how all these things is interpreted. It seems like until basically in the early 2015s, it was a very flat kind of situation, and then you have some kind of a rise. And of course, in the end of the diagram, you always have to be cautious, how you interpret those things because you don't know what the future holds. In summary, we can say that geodiversity and geoheritage research in general, in any mainstream scientific research outlets, showing an increasing and dramatically rapid increase. If you look at the countries, you can see that, for instance, Brazil, which is one of the country where, you know, the tropical rainforest and other kind of conservational issues exist, is one of the top of the list where most of the research come from. And you can see the United States, the United Kingdom, Poland, Spain, Italy, China, Portugal, Austria, and Germany, topping the top of the list of those researchers. If you look at the document per years, you really again see that around the early 2000s, basically everything very silent, and suddenly a big explosion going on. And you can see that somehow in the early 2010s, something was a little bit up, a little bit going down and going up. If you look again, the document per years is a very steady growth of geoheritage and geodiversity related research on the world going on. Why is it important? It's important because it seems like globally there's a higher and increasing recognition on geoheritage and geodiversity research in general. However, if you look at the global scale and you're actually looking at what kind of research is coming out, you also can say that in the early 2000s is a big mixed bag what you actually can deal with, and you can see why later on is a more characteristic type of researchers actually appear. If you want to define the geodiversity versus geoheritage, you actually can look at, you know, what actually happening in the world. So it must be also admitted that the term geodiversity is frequently being used rather loosely, sometimes being used as a synonym for geoheritage, earth heritage, or geoconservation, or even geology, as a term which is which still not really having a very typical and very characteristic definition at all. This means that we are looking at a research arena where many things changing rather dramatically, and if somebody coming up with something really fantastic and very amazing new ideas, it very quickly can go into the mainstream research. This box, what we call the McKelvey box, showing essentially how geodiversity and geoheritage research is essentially interfere or interconnected with each other. You really can see many keywords which are very common in these days for the sustainable development kind of philosophy, if you really want to look at it. So if you want to understand this diagram, and if you come from the economic geology perspective, it's an identical diagram. You know, what is the geoheritage what we define and know today? Was there loss, damage, and pollution, for instance, and how they compare with the hypothetical geoheritage, what we actually have not been identified. I would rather say not been defined, and probably in the future we may see as a clear geoheritage or geodiversity location on Earth. Very common and very important theoretical concept to compare and distinguish between biodiversity versus geodiversity. I put this diagram, it's a very simple kind of diagram, that biodiversity in one way, of course I'm a geologist, so maybe a biologist would kill me if I say like this, but it's kind of an easy kind of approach, because you know what are your subjects to measure. It could be a species, it could be how many type of rabbits, how many type of certain viruses and certain species, or combination of them, or how biochemically defined entities exist in a given area, a given space, if you want to put in that way. In this way, biodiversity is a rather established concept, you know, how we measure it. On other hand, biodiversity is directly affecting our life, you know, how we actually living. So if you're reducing the biodiversity, we have a less diverse environment to live with, and we have an immediate impact our own health, life, and future. However, geodiversity is a very different kind of things, because you can say it's very similar like biodiversity. You count how many type of rocks exist in a surface, certain surface areas. But as you're saying, you can see in this diagram, the problem arises that essentially what you see on the surface is just one reflection of what the three-dimensional, or better to say four-dimensional reflection of the geological entity expressing to you. So it means that geodiversity is a much deeper and much more complex and less simple things to actually measure, how to actually can measure and how we can compare with biodiversity, because many biologists say the high geodiversity, for instance, is almost a predetermination of the high biodiversity, which is personally, I believe, not really the case. So if you compare, for instance, biodiversity with geodiversity, you can see the abiotic, biotic kind of concept as a clashing concept. The time scale issues is definitely very, very important, the dynamic versus static kind of issue. And you can see that water, oxygen, nutrients, for instance, which controlled by the climatic conditions, are the main control of the diversification of the biodiversity. While in geodiversity, the reflection of the maturity of lithosphere, or the reflection of the dynamic Earth, or the contrasting features or processes versus results expressed by the geodiversity. What does this mean? In this diagram, I just show, for instance, few almost like kind of a snapshot kind of visions, like abiotic, biotic. The paleontology, for instance, one of our main field of within geology, is operating in a very different geological time scale in comparison to normal biological time scales. We are talking about thousands of millions of years. We have, however, catastrophic time scales as well, which can take within minutes to hours. But we have evolutionary lifespans, which take tens of thousands of millions of years. So we can see, for instance, that the landscape modifying events like a major volcanic eruption can completely change the entire environment. And then when the recovery takes place, which is basically in a biotic perspective, as a biotic responses, can completely rejuvenate the entire environment, which has the paleontological record or paleontological geoheritage in its way. And we can say that landscape forming events is obviously changing everything around us. So it means that the biodiversity and geodiversity is somehow working together, but not necessarily in a direct coupling mechanism, but you would expect by intuition. One of the very interesting kind of things, for instance, the time scale issues, which can be a very dynamic and static kind of perspective. For instance, in this map, you can see Northern Africa, that we can see probably 7,000 or 11,000 years ago, was a beautiful green environment. It's a very, how should I say, it's an extremely rich biodiversity hosting environment, while today, Northern Africa is a dry, arid environment. So it means that even in that time scale, which is still out from the general biological time scales, but from the geological sense, definitely much shorter than what you would expect, you could see dramatic changes. So if you look at, for instance, in this diagram, the total rainfall, the vegetation cover, land surface temperature, the water vapor distribution, probably the main driving force for biodiversity essentially functioning, but you never should forget what is the, the underlying geological or abiotic diversity what you are looking at. So let's start with a few examples. For instance, what geodiversity in this way mean? Is it a reflection of the maturity of the lithosphere? For instance, if you're looking at one location where I'm now living and working in the Arabian realm, the Arabian microplate, you really can see that essentially, if you're looking at in a geological sense, the diversity of the rocks and anything what you can associate with those rocks has determined basically something going back to 1 billion or more than 1 billion years time, when essentially Arabia was part of Africa, and you see some kind of a subductions, collisions, island arc disappearance, and so on, amalgamating bits and pieces all together, forming these parts, which essentially being separated by the Red Sea Rift about 33 million years ago, and drifted apart and part of the Arabian Peninsula today. So one can say that essentially the diversity, what you can see, for instance, in the middle part of the Arabian Shield, is a reflection of the maturity of the lithosphere. But as I'm a genuine New Zealander, I lived in New Zealand for nearly more than 20 years, I can say that geodiversity also could be a reflection of the dynamic Earth itself, because when you are living close to a plate margin, or essentially where the specific plate interacting through a large transform fault system called the Alpine Fault with the Australian Indian plate, you really can see that along those zones you have a higher number of certain geological features what you can map. And you can say that essentially the geodiversity also could be a reflection of the dynamic Earth. And if you go to the Himalaya in India or Nepal, you really can see all these things happening in front of you. If you go down to Chile, where the subduction went through of 4 stages of completed stages of subduction system, you really can see that all those rocks essentially assembling a very narrow path of certain arc volcanism. So it means that magmatologically, you are looking at an extremely high diversity region in these areas. I have to introduce some word about the geological map, because you can see that, yeah, well, that's all good, it's nothing new what I'm saying, but how all these things can be measured, how we can express. And I'm a geologist, and I actually worked in geological mapping from Libya, from New Zealand, from Central Europe, from Chile, and so on. So I've seen many geological maps, and I've been part of many geological mapping projects, and I can see, as for a geologist, the geology map or a geological map is the key of the information, because the geological map showing you the distribution of certain rock types and their structural connections. So essentially, the geological map could be or should be one of the major things to start to understand geodiversity. So the geodiversity also can be expressed by the process versus result kind of perspective or concept, where the process is associated with those geological processes which forming the geological record, what you can actually map through geological map. And the processes, when you actually looking at the result, how those features essentially form. In this diagram showing this kind of conceptual framework, how certain textural works, what you can see on rocks in a pyroclastic rocks like vesicles, minerals, pyroclastic type, vesicle shapes, mineralogy, and so on, all the way up to the volcanic province mapping, where you can identify, or you can, based on your textural observation, the volcano type clustering, for instance. And all these things can yield for you to see something about the processes which generated them. So essentially, it's almost a matter of taste how you approach to define geodiversity through processes versus results. And then if you are looking at from this perspective, we cannot really neglect the ecosystem services or versus geosystem services to establish and understanding what those systems essentially provide for our living, for instance. So what is the regulating, supporting, cultural, knowledge, and provisioning role, and how those essentially go to the goods and services kind of system, and what the geodiversity stands behind, how the geodiversity essentially controlling these 5 predefined characteristics. Of course, this is more of kind of a planning or understanding the system perspective of this. That's why they approaching from the ecosystem services, but they have been used by Murray Gray, the geosystem services concept, which specifically looking at what geological features essentially for a mode. So anybody can ask, what is the approach to measure geodiversity in this way? So in this book, which is the GeoHeritage book with Reinhard and Brila, published in 2018, and the second edition will come out probably in these days, rather soon, an updated version. I highly recommend to everyone to actually looking at it. you can see, for instance, what is the set of criteria to improve the decision to choose a research method to evaluate the geodiversity. Why is it important? It's important because if my question is that I want to actually measuring the geodiversity from the perspective of conservation, that's probably very different than if I want to measuring from geoeducation or from understanding of the geological system behind them. So this diagram, for instance, showing all those things that you can, for instance, from the spatial range, you also have to define that you are looking at from the local, regional, national, continental, or global perspective when you want to say. This is almost like a pre-flight manual, you know, what to look for or how to actually setting your questions, because when somebody asking a project, for instance, generate a geodiversity map of the Arabian Peninsula or generate a geodiversity map from one specific location, obviously all these questions has their special meaning. The geodiversity assessment methods is the next things. You know, how we actually doing. There's a qualitative methods, there's a quantitative method, and there's a mixed method, a quantitative, qualitative methods. Each of them has their own kind of approaches. The qualitative method basically is more like you go to the field, you're actually looking at what's there, you put your expert opinion, you're sharing with all the experts, and actually on the basis of that, you're coming up something. This is with this diagram showing like descriptive documentation of certain sites. You make an expert classification, you try to expand your site and asking people, more and more people, what they think about, and you're looking at for the values and benefits, and the way you are able to come up some kind of a geocoding or valuation system. The quantitative method is basically a blind method. You're choosing some kind of an indices, which could be a geodiversity, other, or landscape metrics, and you're actually coming up with some kind of a statistical model and spatial aggregation, which producing a map. The quantitative methods try to combine all these things, and there are lots of criticisms for the approaching to that way. I must say that I'm actually pretty much on this side, that in the end, this method providing a direct evaluation and quantification and appointing certain sites, which can be geosites for future references. Of course, if the geodiversity measured in this way, you use geodiversity indices, landscape metrics, and other indicators, and you have seen from Serrano and Ruiz-Flañó papers that the geodiversity index is basically a mathematical expression. This is very good because if you have this kind of expression, we actually can measure certain things. The question is always, is the things what we're measuring is really the right thing? So it means that if you come back to the previous slide, obviously you can see in this hierarchy level that you have to question yourself if you scaled rightly, you know, your measurement and how that number and what that number actually representing. If you're looking at it in this way, it means that the geodiversity estimates offering a huge opportunity, basically to using modern and advanced technologies like GIS, for instance. This diagram showing all those kind of diagrams, and you can see in here that, for instance, geodiversity maps can be created in a way of some kind of grids. You can assembling all those variables, and you're creating this kind of a grid-based maps. You can make a much more smooth kind of statistical methods to generate and highlight where are the highest number of those specific indices what you actually identified before. The key in this way that none of this map actually the ultimate goal or the ultimate answer for anything about geodiversity. So in this way, the geodiversity big questions, you know, what makes an element of geodiversity exceptional, for instance? How should the high value of geodiversity elements be identified and characterized? And how and why should geodiversity, geoheritage be assessed? These are very fundamental questions, and many times coming back to our criteria when you're looking at. So you actually can make geodiversity elements from the usage perspective, from the scientific, educational, geotourism or recreational perspective. And this almost intuitively, you can see that each of them has some values. If you look at in the geoconservation and the nature diversity perspective from the Birilla model, you really can see that geodiversity and biodiversity is one-to-one. And you really see that scientific value in this system is highly emphasized. However, you can see here what actually does mean. Because scientific value, I mean, right now in Samoa, in the Southwest Pacific, where the Western scientific values may not be coincide very well to the scientific values for the traditional Polynesian understanding of science. And you can say that, yeah, well, because that's not science. But no, actually, these people are here for 3,500 years. They cultivated the lands. They understand their end landscape. They knew exactly what to do when tsunami comes. So that's science. So actually, in these parts, there's a lot of discussions in these days what we need to consider carefully. This is this diagram actually showing basically again how you can systematize all these things in a nice way. You can see that the in situ and ex situ elements also have to be incorporated in this way. If you're looking at from a scientific use, representativeness, the integrity, rarity of scientific knowledge, by educational use, the didactic potential, the variety of geological elements, accessibility and safety, for instance, how to visit them, are key. From the geotouristic or recreational perspective, obviously the scenario is a very thing. So if something is flat and boring, you can't really do for that too much for geotourism. But if you see it as an accessible, safely accessible, and is really telling something in a very interpretative way, it has a high potential. Of course, you can build any kind of great system for that. And now I just entered into the second or the last part of the presentation. The IUGS, for instance, started a very important progress, essentially under the International Union of Geological Science, the Commission on Geoheritage and Commission of the Subcommission of the Geological Heritage Sites are really actively trying to locate on Earth those sites which has these high values and incorporating all those things what I just said before. It is not really important. So the first 100 IUGS geological heritage sites has been completed, and it has been announced in the IUGS 60th anniversary event. And the IUGS geological heritage sites are the key place with geological elements and/or processes for scientific and international relevance, used as reference and/or with substantial contribution to the development of the geological science through history. It was declared in Zumaya, which is in the beautiful geological heritage site. And all the selection was incorporated in the first stage by international corporations, by major learned societies. In the first cycle, you can see 181 applications from 56 countries has been lodged, and the first 100 has been selected by the basis of the voting member scoring, the geographical distribution, and the typology. You can see on this map that essentially the first 100 was quite well distributed and really nicely separate, representing what you can see on Earth. You can see here that the total and the first what kind of subject areas. I'm a volcanologist. You can see 5 volcanologist sites has been nominated, which is representing 11% in that way. It means that essentially the first 100 process was a massive success, representing what are the key sites. The second 100, which culminated in an announcement in August last year, is essentially followed the same footstep like the first 100, but more emphasis on the recognition to our science as geology, has a significance for understanding our Earth or Mother Earth in this way, recognition of the scientists who actually work for that, and a further appreciation and preservation of all those things, and essentially all these things together in the spirit of the collaboration of science. There was a new definition as standards, which actually you can see in this slide, and an expanded number of cooperating parts, for instance, the International Association of Sedimentologists, representing a large number, 17 international learned societies, and from 174 countries, 64 countries has been selected on this process. You can see that the evaluation is not so simple because people going through, or the proposals went through a certain evaluation, and you have to have at least higher than 3 to be considered to be accepted in this range. And you can see this distribution pattern very nicely on this way. And as an end result, the second 100 IUGS geological heritage sites being a great success. And if you compare the first 100 and second 100, you can see the certain subject areas and fields represented here. This is just to see the 53 countries which has been identified for the second list. That is a large number of countries, but normally you would not think that they there. And if you combine the first 100 and second 100, it's a truly global distribution of geological heritage sites, what you can see. And you can go to the website and you can browse by the certain number of those sites to actually explain, which the second 100 has been announced in Busan, in the IUGS Congress, in the International Geological Congress. And this was also some kind of launching for the third 100, which is on the way right now. And you can see that we are hoping that the announcement will take place in next year. But this is only one major geological contribution for the geological conservation, geological heritage preservation. But there are many other initiatives, like an International Union of Conservation of Nature, or IUCN, which announced the key geoheritage sites program. But I really hope that it will take off very well and we will be successful progress, because the IUGS 100 progress is essentially restricting basically those top sites. But there are many, many sites and many people, many groups, like a small village in Slovakia or a small village in somewhere in Java, who actually feel that what they have there in a background, that's very important, that they want to prevent and promote. So this program could be one of their key. I also would like to, and this is like a closing slide, we're actually running out of time, that there are many ways to actually be engaged to understand and do research on geodiversity and geoheritage, and you actually also can promote and publish something. I'm very happy to announce that our book with my Ukrainian co-author, The Geodiversity of Samoa, is just published this morning officially. And you can see Springer done, and they have a specific series which actually really focusing on looking at for those sites. And I really would say that many of you may think that, yeah, we all know this, we have the geological, we have this, we have 40, 100 years research history. Yes, that's right. But try to write that down together in a way to present a coherent work, which summarizing from this perspective. That's a very, very difficult job, and that's a science itself. So this is basically the message what I try to close in here. And thank you for all your attention. That geoheritage and geodiversity research is a dynamic and growing research arena. And for Mother Earth, or Gaia, I think this is one of the things what we could look for. And as Dragana pointed out, geosciences essentially have running special issues in this way and have a special session for that. So anybody who do any research like this, most welcome to submit them. Thank you very much.
Thank you, Professor Nemeth, for your wonderful presentation. I hope that our attendees enjoyed it. I checked Q&A box, and since there are no any questions, I think that we can continue with the Professor McKay's presentation, but I encourage you, Professor Nemeth, to keep an eye on the Q&A box. Maybe someone will write some questions so that you can reply. So before I hand the floor to Professor McKay, I would like to just briefly introduce him and to say that he is director of the Griffith Climate Action Beacon at Griffith University in Queensland, and he has a PhD in plant ecology from the Australian National University and over 300 academic publications in the fields of climate change research and biodiversity, as well as related topics in environmental science and policy. Professor Brendan was the coordinating lead author for the 2022 Intergovernmental Panel on Climate Change IPCC 6 Assessment Report, and he was also a member of the core drafting team for the Earth Charter. Let us now hear from Professor McKay. Professor McKay, the floor is yours.
So, is that working, Drago?
Yes, Professor McKay, everything is working.
Okay, and you can still see me. So
yes, right.
So first of all, happy Earth Day, and thank you for inviting me to give this presentation. I've entitled it The Science of Interconnectedness, a science perspective on ethics, multi-species kinship and duty of care to future generations, because one of the reasons we have Earth Day is to make people think about how we should be caring for our natural environment and to help make sure we have a healthy and flourishing Earth system. So that's what I want to talk about today. It's definitely a science talk, but I'm also going to be making some reflections that are perhaps more of a philosophical nature as well. And I also want to say something towards the end about what this means in terms of governance, how we can be or should be thinking about managing what humans are doing in their interactions with the Earth system. So I know everyone knows this, but I just wanted to go over my understanding, at least, on when I say something scientific, what do I mean? Well, I really mean there's some knowledge which has been derived using the scientific method, and I've got three well-known scientific people there. The first is John Dewey, the second is Madame Marie Curie, I think won 5 Nobel Prizes in science, and of course Charles Darwin. And I quote John Dewey here from a 1929 book of his: "Science identifies objects based on intellectual construction rather than common sense. Science converts intellectually constructed objects to data and then goes on to quantify the relationships between these objects and other phenomena considered to be causal factors." Which is to say that the focus of scientific research is on theories about the causal factors that explain the relations between intellectually constructed objects, and then seeks to identify situations that can test the validity of these theories by experimentation and empirical confirmation. So Madame Curie, of course, did laboratory experiments. Charles Darwin did, if you like, natural experiments. So did Einstein. They had theories which made predictions that could be empirically tested by going out and taking observations in nature. So why have I gone over kind of a basic definition of well-established definition of what the scientific method is and what we mean by science? Well, the emphasis here is really on theory. If we're saying something is scientific, then it means we have a scientific theory about it. So at the core of science then are some kind of mathematical or quantitative models of relationships or processes between objects, however defined, and theories that explain their past and current responses, and also make predictions about future behaviours or responses. Well, the question I want to ask really as the starting point for my presentation is there a scientific theory of life? Right? Well, despite all our scientific advances, we actually lack a scientific theory of life, i.e. how life formed from non-life. some people might actually ask whether that difference matters, and I've got more on that later. But I think it's quite remarkable that despite our extraordinary scientific advances, we actually still lack what I would call a comprehensive scientific theory of life. We do have scientific theories of the universe, cosmology, the evolution of life once it's formed, and of Earth planetary processes, as we just heard about, atmosphere, biosphere, ocean interactions with respect to energy and chemical substances, and also how these enable and support life. And we also have another source of knowledge called traditional knowledge of Mother Earth, which I am going to do a little comparison of later on towards the end of this talk. But to begin with, I want to talk a bit about those scientific theories we do have about Earth and what we do know scientifically. Well, as I'm sure you're all familiar with to some level, we have very good scientific theories about cosmology, the birth of the universe, if you like, and the birth of Earth. The current understanding is that about there was an event which is popularly known as the Big Bang, and about 400 million years after that, the first galaxies had formed, and in the billions of years since then, stars, galaxies, and clusters of galaxies have formed and reformed. Eventually, one of them yielded our home galaxy, the Milky Way, and our cosmic home, the solar system. This theory was proposed by Georges Lemaitre in 1927. And then in terms of Earth, we have what's called the solar nebula disk model, which was proposed by Pierre Laplace in 1755, where the solar system is formed from gas and dust orbiting the Earth, and the planets formed, and all its elements came from consolidation of this cosmic dust and subsequent planetary processes. So we are all made of cosmic dust, it turns out. And of course, once life on Earth had began, thanks to our geologists and our paleontologists, we've developed this incredible observational data set from the fossil record of the evolution of life on Earth, which started about 400 million years or so after the formation of the planet. The first life evolved, single-celled organisms, and about 3.2 billion years ago, the earliest photosynthesizing plants, which we'll talk a bit about later. After a considerable period of time, 2.5 billion years, there was a first major increase in atmospheric oxygen levels and a glaciation event. And on we go until about 500 million years ago, we had this Cambrian biological explosion where animals really started to come about. Land plants, the first vertebrate land plants, non-avian dinosaurs. Very, very recently, the first hominins, about 2 million years ago. And maybe about 200,000 years ago, the first humans. But we have this extraordinary, incredibly well-documented record of life on Earth. How did that come about? Well, we know that is from the theory of evolution, which was articulated or developed and articulated by two people in parallel. Charles Darwin, who got all the limelight, if you like, but also Alfred Russel Wallace. And the theory of evolution basically goes like this: change in heritable characteristics of biological population that are expressions of genes passed on from parent to offspring during reproduction. That's what evolution is biologically. Different characteristics can arise in a population due to mutation, genetic recombination, and other sources of genetic information. Natural selection and what's called genetic drift, just random genetic change at birth, act on the generic variation in a population, resulting in some characteristics becoming more or less common in the population. And and evolutionary pressures such as changing climate and other physical environmental conditions can result in natural selection, causing some traits to become passed on and others to fade away. And these evolutionary pressures change over time. But Darwin and Wallace's theory of biological evolution, which has been, again, substantiated through modern genetic studies and over 100 years of research now, still does not answer the question of how did life begin? How did life go from non-life, from physical things that were just chemistry, to living things? Well, the current theories around that really relate to what are called the preconditions for and the precursors of life. And these were really physical objects and physical processes. And there were two really critical ones. The first is the fact that Earth has a molten core and it spins on its axis. And as a result, Earth is surrounded by an immense magnetic field called the magnetosphere. And the magnetosphere has this wonderful property of deflecting deadly solar winds. So if it wasn't for the magnetosphere, life on Earth, as we know it, would be impossible. It just could not exist. So if you like, the first precondition for the generation of life on Earth was these physical properties of our planet, a solid inner core, a outer liquid core, and a spinning Earth, which creates the magnetosphere. Thank you, magnetosphere. Without you, we wouldn't be celebrating Earth Day today. But there's a second precondition, or really it's more of this is a precondition. The next is really a precursor, because the precursor to biotic metabolism, the production of chemical compounds and substances, was abiotic metabolism. And because this produced the chemical precursors of biological metabolism. And I like to think of these being born from the bowels of the Earth. And again, I'm sure you've heard about this in popular science to some extent. But at the bottom of the oceans, there are what are called hydrothermal vents, which is a result of seawater percolating down through fissures in the Earth crust in the vicinity of spreading centres of subduction plates, i.e. places on Earth where two tectonic plates move away or towards one another at the bottom of the ocean, many kilometres deep, thousands of metres deep. The cold seawater is heated by hot magma and re-emerges to form the vents. And seawater in these hydrothermal vents may reach temperatures of over 700 degrees Fahrenheit. Organic metabolism, which is the chemical substances that are produced by life forms, evolved based on the chemicals generated by this mantle crust ocean processes. So ecosystems formed from and which are dependent upon these chemical processes resulting from geophysical processes, the interaction from geodiversity, from the interaction of seawater and hot magma associated with underwater volcanoes. Life that evolved from the bottom of the ocean to land, and once it worked its way up the ocean, it started engaging with sunlight and became dependent upon solar energy, sunlight as the photons that are in solar radiation, for the energy to drive that biological metabolism and to support ecosystem development. So if the Earth didn't rotate, if it didn't have an inner and outer magma core, there would be no life on Earth. These were the preconditions and the chemical precursors of life. And then biological evolution took over and we refer to that as the tree of life. And again, the current scientific theory, states that all life on Earth evolved from a single common ancestor, and all species are related to all other species through inherited DNA, including us. So every species has a last common ancestor with every other species. And if you travel back far enough in time, in the evolutionary sense, in the evolutionary tree, and all forms of life share a last universal common ancestor, which likely evolved in deep sea vents about 4 billion years ago, as we were just discussing. So Homo sapiens, our species, and gorillas and orangutans and chimpanzees, we did not evolve from them. All of us had a common ancestor back in time, and not that far back in time either. So here's a little test. If this was a class, I'd ask you to write down your answer, but how much of our genes do we share with others? So a chimpanzee, just have a think for a moment, or think to yourself, answer to yourself, how much of our gene, what percentage of our gene do we share with chimpanzee? That's a fruit fly, and that's a bowl of rice grains, white rice grains. So just answer to yourself, what percentage of our gene do you think we share with chimps, with fruit flies, and with rice? Well, with chimpanzee, it's 99%. Think about that, 99% of our genome, human genome, is the same as chimpanzees. Fruit flies, it's an awful lot, isn't it? 60%. Us and fruit flies have 60% of our genome in common, our genetic makeup in common, our DNA. What about rice? Well, it's actually 25% rice, which I think is quite extraordinary. So this again helps illustrate the reality of the tree of life and just how interconnected we are with all other species, all other forms of life, currently alive, all other forms of life that have evolved and gone extinct in the past, and all those species that have yet to be born. We all come from and are part of the same tree of life. But wait, there's more. We also have clear evidence. Again, this is we have our geophysicists and geochemists to thank for this, because we also have now very clear evidence for what is referred to as the coevolution of life and Earth's chemical environment. And this is easily understood if we just step back for a minute and just think about what living things do. So every species of life, bacteria, fungi, plant, and animals, has to take in essential chemical substances, retain them in the necessary concentrations, and release waste substances and exclude toxic substances. We do that. Every living thing does that. And it's also true that one species' waste can be toxic to species, so they must either exclude them, evolve so that chemical substances are no longer poisonous, or evolve so they become a source of nutrition, energy, or essential for metabolism. And the really incredible example we have that is oxygen. So if you go back to early in the history of our planet, our atmosphere had very little, if any, oxygen. And now, of course, we have a lot of oxygen. Well, what happened was, and this is a paper by a geochemist, Robin Williams, published some time ago now, where on the bottom axis, it shows you time in a log scale in billions of years before the present. And the vertical axis is the fraction, well, it's the oxygen level. It's the fraction of oxygen in the atmosphere at that time relative to the present atmospheric level. So that you can see about 3 billion years ago, it was the start of photosynthesis. Well, at the time, for most all the other species that were on Earth at that time, oxygen was toxic, right? Oxygen was either toxic or was not a resource they could use, and the oxygen that was produced by these cyanobacteria was just a waste product from their metabolism. But that over time, the level of oxygen increased so much in Earth's environment that the vast majority of species really, had to evolve, or it did evolve, so that they used oxygen, and it became an essential thing. So the chemical composition of Earth's atmosphere is certainly not just a function of physical processes. The chemical composition of Earth's atmosphere co-evolved with the bioevolution of life. So we talk about the co-evolution of life and Earth's chemical environment. So we can say that all forms of life evolve and persist and continue to persist as part of a co-evolving planetary ecosystem. Whether you're blue-green algae or a killer whale or people, we're all part of that same planetary story. Now, I mentioned that there's not a scientific theory that explains the origin of life. We've got a pretty good idea of where life started at the bottom of the ocean, and that these precursors, chemical precursors, the chemical metabolism that went on at the bottom of the ocean produced these chemicals upon which life formed. We still don't actually have a theory which explains how he went from there to living organisms and ecosystems. But people have been thinking about it for a long time, and one of the first people to document it in a modern scientific sense, or to propose it, was James Hutton, who was actually the founder. I actually think he was the founder of the discipline of geology in Great Britain. And he wrote this wonderful paper, which you can still find online, called Theory of the Earth, or an investigation of the laws observable in the composition, dissolution, and restoration of land. So he saw very clearly what I just said, that he didn't think it was valid to separate physical processes and biological processes, because they're so interconnected. If you wanted to understand Earth, you needed to look at them both together. And there are others who also have really focused on that idea. And I think one of the most influential and insightful was a Russian geophysicist, Vladimir Ivanovich Venensky, who in 1924 wrote a book called The Biosphere, Life as a Geological Force, where he talked about the biosphere being all those components of Earth's system that are influenced by life, whose chemical composition is a function of that coevolution. So the biosphere for Venensky was not just the living beings on Earth, it was all the parts of the Earth system that they chemically interacted with. So that included the atmosphere, it included the ocean, it included the land, at least as far down as the rooting zone of ecosystems. But more than that, because he also recognized about fossil fuel, coal, oil, and gas, that life had also had become fossilized, and also when you look down into sedimentary layers, you could see the how life was also embedded within so much of our hard geology as well. And also the bottom of the ocean, obviously the sediment of the ocean as well. So when he said, when you added it up, an awful lot of the Earth was, from his point of view, the biosphere. He wasn't as influential as I think he should have been, because his work was not published in English until after World War II, when there was a couple of papers he co-wrote with some American researchers, and they didn't use the term biosphere, they used biogeochemical cycling. And so I think it's been unfortunate, because it would have been nice if we had if that book had been published in English in the 1920s, and we were using the term biosphere in the in the way that Venantsky had intended. I think Arthur Tansley made a great contribution too, a British ecologist. He invented the ecosystem concept, which was explicitly about the biotic physical systems interacting, not at a planetary scale, but at kind of all other scales. And James Lovelock, of course, and his Gaia theory, where he talked about Earth functioning like an organism in many respects. So James Lovelock was a very interesting guy. He's an independent researcher. He developed an instrument that NASA used when it sent satellites or spaceships and sent instrumentation to look at Mars and Venus. And he developed an instrument that enabled them to that enabled the chemical composition of Mars and Venus to be sampled and measured. And he actually did the analysis. And what he showed was just how fundamentally different the atmosphere of Mars and Venus and Earth was. And the only explanation he could find for that was the coevolution due to life and the difference that living organisms had on the chemical composition of Earth. And that was the basis of his Gaia theory, which is all about looking at Earth as a co-evolved system and the kind of feedbacks that are put in place. So we actually have quite a long history, I think, of scientists thinking about Earth as a co-evolved system. But actually, there's a number of others who also recognize this. And I mentioned this woman who was a philosopher, Margaret Lucas Cavendish, a 17th century philosopher. And she actually thought that, of course, most science was done by men back then, that men were being a bit arrogant in thinking that, they're so special that they're different from the rest of nature. So this is a famous quote of hers: "I perceive man has a great spleen against self-moving corporal nature, although himself is part of her. And the reason is ambition, for he would fain be supreme and above all other creatures as moved towards the divine nature. He would be a god if arguments could make him so." So she was arguing that, yes, and we're just an animal, and there's lots of other animals, and we're not so special maybe. And Alfred North Whitehead is an interesting scientist too. He was a physicist, a theoretical physicist and mathematician, very sophisticated thinker. And he was not dismissive, he I guess argued that we shouldn't make such a strong distinction between physical processes and biological processes. He think we should think of everything as being organic and material. I've got a quote there: "Recognition that the world is organic rather than materialistic is essential for anyone wanting to develop a comprehensive account of nature. The result is that nature is no longer thought to be simply atoms in the void, but instead a structure of evolving process. The reality is a process." He was talking about a continuum of processes, and that we shouldn't kind of put anything particularly special on this divide between life and non-life. So we've got lots of scientists and components of a theory that says, Earth is a co-evolving system, but still, what kind of co-evolving system? It's certainly not a simple system. Here's a simple system. It's a car engine, right? Internal combustion car engine. I could have had an even simpler one, which would have been an electric vehicle motor, which is even simpler. So a car engine is complicated, but it's simple, controllable, and predictable. If you're a good auto engineer, you can completely take that engine apart into all its component elements, and you can put it back together again if you're a good auto engineer, and you can predict exactly what it will do, and you can press the buttons and pull levers, and you know exactly how to control it. But Earth's not like that. Again, there's a branch of systems theory which has come up with this concept of complex adaptive system. There's been a lot of work done in Europe and in the USA in a couple of institutes. The Institute for, I forgot the name of it, IIIAS. Anyway, there's a Santa Fe Institute, there's one in Austria, there's one in USA, who have been working on this concept of complex adaptive systems. So complex adaptive systems, I've got a little animation there. It's actually from a PhD student's thesis, but I just like it. It's a little GIF. Complex adaptive systems have emergent properties not predictable from constituent components. It's got feedbacks. They can be positive that reinforce a trend or negative that dampen a trend. They can have top-down as well as bottom-up processes. And the bottom-up are the result of the interactions of very large numbers of agents, organisms, like Earth's atmosphere becoming oxygenated was the aggregate effect of the interactions of billions of organisms over a long period of time. And they have certain system qualities around stability, resilience, adaptive capacity, and autopoiesis means they're self-generating and self-maintaining. So, what Lovelock was about was, he didn't use this terminology, but these days we would probably describe Earth not as Gaia, but as a complex adaptive system. So I've got here another philosopher, another English philosopher too, Mary Beatrice Midgley, who studied biology and evolution very carefully, and also kind of earth sciences. And this is a quote from her, that we are not aliens on a strange planet. Our history and biology, which place us here, ensure the facts of this planet have plenty of meaning for us. So she was actually reflecting philosophically on if you take biological evolution seriously, if you take what Earth system science is telling us seriously, this really is our home. We actually belong here. So we really need to be thinking about our ethical responsibilities. And ethics just means deciding what the right or wrong thing to do. So in this case, how should we be behaving towards each other and other species and future generations if we accept what science is telling us about coevolution and the tree of life, etc. Well, I want to come back to this idea of Mother Earth because, well predating modern science and scientific theories, the world's First Nations, Indigenous peoples, had their traditional knowledge system, and a foundation of their worldview was what is now more commonly referred to as Mother Earth, or the Mother Earth concept or worldview. And I would suggest that the basic precepts of kind of a Mother Earth cosmological worldview are actually well aligned with the scientific theories of life and Earth system that I've been talking about, because the traditional knowledge concept of Mother Earth points to a shared origin of life. It points to the interconnectedness of all life, including humans, and it points to the interdependence of human well-being and that of the greater community of life on a healthy, functioning Earth system. Traditional knowledge uses different language, but I think we can find these points of contact. So I'm kind of coming to the conclusion that the Indigenous concept of Mother Earth is proving to be more than kind of a metaphor or a cultural contract, but it's actually a scientifically accurate description of how life on Earth came to be, our relations to others and interdependencies. And I've got a quote there on the right from Dr. Carrie Arabina, who's a traditional woman from Torres Strait in Australia. I was actually one of her PhD supervisors some years ago now. And this is a quote from her thesis: we're all indigenous to the universe. The universe is moral, the universe is alive, everything is related. Space determines the nature of relationships and time determines the meaning of relationships. Something which, to me, echoes what Alfred North Whitehead was saying about process and reality. So, again, this is Earth Day. We need to be thinking about our ethics when it comes to what we're doing to Earth as our home, and how we're interacting, managing the Earth system so that it stays a place that's suitable and supports our life, human life, and the life of the greater community life, and is a healthy planet for future generations. So, I think a valid question is, what form of governance are consistent with the scientific understanding we have of Earth as a co-evolving complex adaptive system, and what I would suggest is now the kind of scientifically supported traditional knowledge concept of Mother Earth. Of course, the system we have, our system of national governments and the UN system, are not based upon that scientific understanding. We had a lot of those, the scientific theories and traditional knowledge concepts in place well before the UN was formed in the wake of World War II. However, that scientific knowledge did not inform how we have set up our governance at a national or global level. So just to kind of finish up, the problem is if we take what the science is telling us seriously again, Earth is a complex adaptive system. Well, complex adaptive system cannot be controlled like a car engine. It really can only be influenced. And I draw here upon the work that was done by Donella Meadows, who founded the systems modeling research program at Massachusetts Institute of Technology, MIT, which continues to this day. She started that work and developed that approach to systems modeling for the first Club of Rome report, and which was called The Limits of Growth, where they took a systems modeling approach where they looked at system states and inflows and outflows and feedbacks and the like. And one of the conclusions Donella Meadows came to was that a complex adaptive system cannot be controlled, only influenced. So you need to understand the levers that enable you to influence the system. And she came up with 12, which she called places to intervene in a system. I don't have time to take you through them all. You can easily Google, if you Google Donella Meadows, you'll come to her website where the article and these are. But at the least influential one are looking at changing parameters and numbers, influencing positive feedback loops, and then at the bottom, the goals of the system, etc. So to conclude, if we take what our scientific understanding is telling us about how life evolved on Earth, how Earth functions as a complex adaptive system, we need in place, and we're interested and want to and seek to care for Earth in a way that keeps it a healthy and safe for current and future generations. I think we need to be thinking about our forms of governance to make sure they're informed by this understanding. Thank you.
Thank you, Professor McKay, for your presentation. If anyone has any questions, I encourage you to write your question in Q&A box. But so far, there were no any questions. Well, I want to thank you, both of you, for your insightful presentation, and I want to thank to all our attendees for joining us today. And I hope that you found the session informative and engaging. Recording of the webinar will be made available as early as possible at SciForum. And happy International Mother Earth Day to everyone. And until next time, take care and goodbye.